Now we're going to start talking about energy, which is obviously a huge topic in physics. We're going to start with sort of a simple application of conservation of energy, the conservation of mechanical energy. And in order to use this, I think it's really important that you identify these sort of four key concepts and keep their definitions in mind as they come up. Okay, so the four key quantities. Well, one isn't a quantity. I don't know. Let's call it that. Okay, the first one is the kinetic energy. And I'm going to go into all these definitions pretty soon. Kinetic energy is the one that we've already seen because in elastic collisions for conservation of momentum, we use the fact that the total kinetic energy was unchanged by the collision. And I'm going to always represent kinetic energy as the capital T. The second one is the work, which I'll represent with a capital W. That makes more sense than a capital T for kinetic energy, but as usual, I don't get to make this stuff up. I just use what other people have. Anytime it doesn't make sense, I usually think maybe something in Latin or something. Maybe that's what the explanation goes back to. The third one is not really a quantity, but it's a description of certain types of forces. And so you want to remember what this means. Conservative forces. And the fourth one and the last one that you want to keep in mind through this whole discussion is the potential energy. And I'm going to represent that as a capital U. Okay. And now, before we get started with the work of defining things and stuff like that, I'm going to give you the sort of punchline first. The key result that we're working towards is the conservation of mechanical energy. And this is what it says. If the only forces that do work on an object are conservative forces, then we can use this equation that says the total potential energy plus the total kinetic energy at some instant is equal to the kinetic plus the potential energy at any other instant. Okay, so there's the big equation that we're going to use. And we're going to see that it's useful for coming up with relationships between objects' location and their speed, which is useful sometimes. And so when we talk about conservation of mechanical energy, we're thinking of this sum of potential and kinetic energy as being called the mechanical energy. And what this law says is that under these conditions, this sum of potential plus kinetic energy doesn't change. Okay, so now that we have this big result, the result that we're going to be using, I have to go back and define some of these things. You saw the four things that I told you are going to be important coming up. Kinetic energy, potential energy, conservative forces, and then work both came up in figuring out whether you had a case where you could use this equation. Okay, so I'm going to start with the one that we've already seen, kinetic energy. Kinetic energy of an object is defined as 1/2 times the mass of the object times its speed squared. Okay, speed, I'm going to use that capital V that I've used before to represent the speed. And so what this says is the bigger, so if two things are moving the same speed, the thing with the bigger mass has more kinetic energy. And for a single object whose mass doesn't change, as it speeds up, the energy increases. And so that's really what we're going to think of, like, so for a single object, and for normal objects, the masses don't change as they move around and as time goes by. So as an object speeds up, its kinetic energy increases. That's really kind of the simplest way you can think about how kinetic energy works. And we've already talked about the units of this, but the units of all of these types of energy that we're talking about are going to be the same. And you can represent it a couple of different ways. With kinetic energy, if you use this equation to come up with the units, you get kilogram meters squared per second squared. Well, 1 Newton is a kilogram meter per second squared, so you can also, often you see this represented as newtons times meters. Those are the same thing. And since we're going to use energy so much, and these are both sort of cumbersome to work with, we're going to call this unit a joule, and we'll represent it with a uppercase J. Okay, so that's kinetic energy, just this formula right here. Next, we're going to spend a little more time than that thinking about this idea of work. Kinetic energy, let me put this T in here again. So the work, this is going to be a capital W. And kinetic energy is an amount of energy that an object has. Work is not an amount of energy that an object has. It represents a change in energy. So work is a change in energy caused by the application of a force. Okay, so I'm being specific about the fact that this is only caused by application of a force, because there are other ways to increase an object's energy that we'll talk about when we talk about thermodynamics. If you heat an object up, it gains energy. If you apply electric power to an object, it gains energy. It can gain energy in various ways. But we're just talking about energy that's changed by applying a force. Okay, so to calculate this for an object moving along a line, we're just going to think of it like this. The work is equal to the force times the displacement. Okay, and notice that both of these can be positive or negative, and you include that positive and negative in your calculation. Okay, so let me label these. This is the displacement of an object. This is the force on an object. And so you want to notice right away that no matter how hard a force is pushing on something, if there's no motion of the object, there's no work done. Okay? So you should notice that work is done only when an object moves. You know, that's a little bit of a funny idea when we're used to thinking about forces, and you can apply big forces to things that don't move, but it's not the same now that we're talking about energy. So work is done only when an object moves. And so let's think about kind of intuitively what to make out of this. And as we do this, it's going to be important to keep in mind that kinetic energy represents the speed of an object. So in this intuitive result, I'm going to be looking at an object and thinking about how a force could speed it up. That means increasing its energy. What kind of forces would not make any change in the object's speed? That's an object that, you know, doesn't change energy at all. And then last, what kind of forces you could apply to an object to slow it down, which means reducing the energy. Okay, so the first intuitive result is if this force F, you know, if this force F is within 90 degrees of the displacement, work is greater than zero, and the energy, in other words, increases. Okay, so let's think of an example. Let's say that our object is this cart that's moving along the floor. Okay, and let's say that the object is moving this way. Well, an example of a force that's within 90 degrees of that, the direction of that displacement would be like, okay, what if we applied a force like this to the object? Okay, if we put those two tail to tail and used a protractor to measure them, you'd get an angle of less than 90 degrees. And you can sort of see why that is. Like, this is a case where we're saying that a force like this increases the energy. Well, yeah, if this thing is moving to the right and you apply a force that, you know, has a leg of the right triangle that's to the right, okay, then that force is going to cause this to speed up, and that means the energy increases. On the other hand, if the force is greater than 90 degrees from the displacement vector, then the work is negative. We have a negative change in energy, and that means that the energy decreases. Okay, but there's a third possibility, and that is if these two are exactly perpendicular to each other, what happens in that case? Well, it sort of would make sense probably that if you're making a transition from being within 90 degrees to which increases energy to an angle of greater than 90 degrees that decreases energy, then maybe if those two are perpendicular to each other, there's no change in energy and work is equal to zero. And that's exactly the way it works. So if the force and the displacement are perpendicular, then the work is equal to zero, and the force then in that case causes no change in energy. Okay, so if we're trying to make sense out of this, let's think of this same cart. And it's moving, draw that a little flatter. Yeah. And it's moving from right to left. Okay. So the displacement is going to be this way. The velocity at any instant is that way. Well, what happens if you apply a force just straight down? Maybe in your head you might think, yeah, I think that's going to slow it down, but really that's a bunch of friction effects that you're thinking of. If you had a frictionless set of axles on this cart and you applied a force exactly down without applying any side-to-side forces, you would see that the speed stayed exactly the same. It doesn't have any effect on the speed. And so from this number 3, it turns out this is going to be important to us. If a force and the object's velocity vector are perpendicular to each other at every instant, then that force does zero work on that object. There are two cases that we're going to see all the time where this happens. So here are the two most important cases. The first one is the normal force, the pushing force from the surface in an object that's either rolling or sliding. Okay. So let's think of kind of my go-to example in a lot of cases. Let's just think of this cart that's moving to the right. The normal force, like, okay, so this is the direction that it's moving. I don't want to make that part of my free body diagram, but there's a weight force going down, okay? But here's the one we're talking about, the normal force, the pushing force from the ground. That normal force is perpendicular to the velocity vector, and so it never does any work. Okay, and it doesn't matter what the shape of the path is. It could be curved or it could be an incline, but in every case, that normal force is going to be perpendicular to the velocity, and so that normal force does zero work. Okay, why would we care about this? Well, we care about it because in our introduction, when I brought up this conservation of mechanical energy, I was very specific about that only conservative forces could do work. Okay, well, I'm going to tell you about some forces that don't do any work, and so they might help some problems fit into this category. Well, they will. Okay, the second type of force that'll come up from time to time that does zero work is if an object is in circular motion. Any force exactly toward or away from the center of the circle. Okay, so let's say that we have an object moving around a circular path like this. Let's say that the object is here on this circular path. We know that the velocity vector of that object is this. Let's say that there's a cable connecting this object to the center of the circle. That's a pretty common situation. Then the force applied by that cable is along that line toward or away from the center. And you can see these two, the velocity vector and that cable force, are perpendicular to each other. So that cable force, no matter how big a force it is, doesn't do any work on this object. Okay, the SI units for work are, like I said, units of joules. Even though this is a change in energy, not an actual energy, still a change in energy is just subtracting two energies, so you get the same units. The next thing we have to talk about is this idea of conservative forces. So I'm going to think of this as, how do you differentiate between conservative and non-conservative forces? Well, a conservative force is one where if you know the object's location, that's enough information to know the force applied to it. Okay, so if you could come up with a spreadsheet or something where someone would punch in a location and it would spit out the force, no matter what the object's doing, then that's a conservative force. So, okay, a conservative force is one where whatever the object is doing, knowing its location is enough to know the force. Okay, well, what are some examples? The easiest example is the weight force on an object. If you know the object's mass and somebody tells you the location, you can tell them what the weight force is. In fact, they don't even have to tell you the location. The weight force is going to be the same no matter what the location is, but we don't care about that. That it's still conservative. It's just kind of extra conservative. Another example of a conservative force is if you attach, say, a spring to a wall and attach the object to the other side of it. Okay, we talked, and then you move the object back and forth, stretching and compressing the string. Well, the spring. We talked about the fact that the way a spring works is if you stretch it, it's going to try to shorten itself back to its resting length. And if you compress it, it's going to try to lengthen itself back to its resting length. And so no matter what you do with this object, if you measure the length of that spring, which is the equivalent of giving the location of the object, then you can calculate what the force is. It's always going to be a magnitude of K times that deformation. Remember that equation? And then just in the direction that would bring the spring back to its resting length. And in this class, those are the only two conservative forces we're going to use. And so if you want to ignore, well, I don't recommend this, but if you want to ignore the meaning of conservative forces and just remember that these are the two conservative forces we're using, that would actually work perfectly well. So there are two conservative forces in this class. And those are gravitational forces, the weight, and the second one is forces applied to an object by springs. So I'll just call that spring forces. When we get to the second term of this class, and we start talking about electricity and magnetism, we'll have to include electric fields in there, and we'll have to include magnetic fields in there. But for this part of the class, the only conservative forces are gravity and springs. Everything else besides those is a non-conservative force, which means that everything besides these that we talk about in this class, you could put an object in a certain location and figure out a way to change that force. Okay, like for example, a normal force. If an object's resting on a surface, okay, there's a normal force that's the surface pushing up on that object. But now if I push my hand down on the object, the surface is having to apply a bigger force to it to keep it from sinking into the surface. And so even, in the case of a normal force pushing up on an object, it can be at that same location and I can cause it to change. Now, conservative forces have something called a potential energy. So conservative forces have potential energy U. And how you calculate that potential energy for different forces changes, but any conservative force has a potential energy. Any non-conservative force does not have potential energy. And the idea of potential energy, and this is the one we're going to call capital U, is that the work done by this conservative force is equal to the negative change in potential energy. So really it's just a way to calculate work. It tends to be an easy way to calculate the work done by a certain force. But this is a really important relationship. You can think of that as the defining relationship of potential energy. Since we only have two conservative forces, we only need two potential energy functions. And so here they are. The first one is the potential energy due to gravity. And so the gravitational potential energy is equal to the mass of the object times 9.8 meters per second squared times y, where our positive y has to be up. Okay. So let's think about the meaning of that for a second. The work is the change in potential energy. Okay, and work is positive if it's roughly in the same direction that the object is moving. Okay, so let's think about a case where gravity is acting in the same direction as an object moves. If you drop an object, okay, it's moving down, its velocity is down, the force of gravity is down, and so gravity should be producing a positive work. That means that the change in potential energy should be negative. So let's see if this formula gives us a negative change in potential energy. Well, you go from mg times a big number to mg times a small number. And so what you get if you take the later potential energy minus the earlier is you get a negative change in potential energy. The second relationship, the second potential energy function that we're going to use is for springs. And the spring potential energy is 1/2 times the spring stiffness times x squared, where x is, so we're going to say x equals 0 is when the spring's at its resting length. Also, look at these and remember that I said one of the important derivative relationships we have in this class involves the potential energy. If you have time, just glance back at that derivative relationship and see if you can make sense out of how it holds in these cases. Okay, we'll talk about it more in the next day or two. Okay, well now, so this is an important result for us. We're going to use these functions in every one of these energy problems. But now we've defined all of the four important things, and we can actually do some problems. So now we're ready for the conservation of mechanical energy. So as an example, let's imagine a person skiing down a hill. And let's say that this hill has a height of 5 meters. And a person starts at the top of the hill Okay, and then skis down the hill, so they end up 5 meters lower than when they started. And they're at rest at the top. And the question is, how fast is the skier moving at the bottom of the hill? At this instant, the person is at rest. Okay, well, in order to use conservation of mechanical energy, we have to know that any force that does work on the skier has to be conservative. So let's think about the forces on the skier. So here's, as the skier goes down, okay, that's an outline of the skier. What forces are acting? There's gravity, but that's a conservative force, so that's fine. And then the only other force is a pushing force from the snow. We're assuming that this is frictionless. And so we have this normal force. Okay, well, that normal force is non-conservative. But the key thing is, remember that I gave you two types of non-conservative forces that do zero work, and normal force is one of them. The other one is forces along the line to the center in circular motion. And so this does zero work. This one is fine because it's conservative. And so this meets our requirements. And so we can use conservation of linear momentum, which says the potential energy plus the kinetic energy at instant 1 is equal to the potential energy plus the kinetic energy at instant 2. Okay, so let's start filling this stuff in. And I think it's helpful to just write out a table so you don't miss anything. So instant 1 is going to be when the skier is at the top of the hill. And instant 2 is going to be when the skier is at the bottom of the hill. And let's start by calculating the potential energy. There are no springs in this problem. There's no spring touching this skier. And so the only potential energy is going to be due to gravity. And that's equal to the mass of the skier times 9.8 meters per second squared times the height times the y position. Well, the y position always depends on what you choose as your 0y. I tend to always choose my 0y to be the highest, the lowest location in the problem. So like here, it's going to be at the bottom of the hill. But you could put your y equals 0 anywhere you want, and this will still work out. Okay. So what that means is at instant 1, the y position of this skier, because I'm also making positive up, the y position of this skier is going to be positive 5 meters. So this potential energy is the mass, which wasn't given, times 9.8 times positive 5. And if you multiply this out, you get 49.0 times m. And now we have to calculate the kinetic energy at instant 1. That's 1/2 times the mass of the skier. Again, we don't know that. Times the speed squared. The skier is at rest at the top of the hill, and so this is 0 squared. And so the kinetic energy at instant 1 is 0. And now we'll go to the bottom of the hill and calculate these. The potential energy is equal to m times 9.8 times the height. I chose my y equals 0 to be at where the thing is at instant 2. So I'm going to, so that makes this y value 0, and so the gravitational potential energy is 0. And then for the kinetic energy at the bottom, we don't know what that is. We're trying to calculate that speed, but we do know that whatever the speed is, it's 1/2 times that unknown mass times the speed squared. And now we'll plug this into the conservation of mechanical energy equation. We have 49 times m plus 0 is equal to 0 plus 1/2 mv squared. Okay, so 49m is equal to 1/2 mv squared. You can divide both sides by m, and that gets rid of these, which just shows that this answer is going to be the same no matter what that skier's mass is. Multiply both sides by 2, you get v squared is equal to 98. And you get that the speed of the skier at the bottom of the hill is 9.90 meters per second. Speed is always positive, so that's how you know it's not the negative one. Okay, so you can see that this is a really powerful technique in some cases. If you happen to have no forces acting on the body that you're analyzing that are non-conservative and also doing work, then it's really just a one-line calculation to come up with a relationship between the object's position, location, and its speed.